In this section, we're going to cover probably, I wouldn't want to oversell this section, but it's extraordinary. This sets up everything we're going to do in the course. So you need to understand this section perfectly. I would test yourself 100 times, whatever. If you understand this, then you have a good shot of understanding the course. If you don't, then the course is going to be terrible. So this is crucial. Anyways, it's so long that it's broken into two parts. Let's take a look at some of the notation first before we begin. When you see this notation, sort of a double strike R, this equals the set of all real numbers. And then in addition, when you see this notation, you may know this is the plane where we call R cross R. If I use R to the third power, this is R cross R cross R. These are the ones you're familiar with. Like the plane, this is just the standard XY plane. Over here is three-dimensional space. So where you would have a Y, you would have an X, and you'd have a Z, etc. And in general, we're going to be talking about R to the N, which is R, X, or cross. We use the word cross. R cross, dot, 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 R, for a total of N times. So we'll do a lot of examples in R2 and R3 because you can visualize them. But then we'll do a lot of work in here when we want to prove general properties of this whole vector situation. So anyways, typically, we can write a vector in R squared in the following way. V stands for vector, and I'll put an arrow above it to indicate that it's a vector. And typically it will look like this. If I do the same thing in R3, a vector will look something like this. So we'll have three components, etc. Rn will have n components and things like that. I'll do more examples in a minute, but let me visualize some of these things inside of here. Now, there's two things I want to do. I want to not only show you a little bit about vectors, but also a program that is very helpful for graphing called Geogebra. So I haven't started it yet. Let me show you how to find it. So let me click into here. And practically, nowadays, you don't even have to go to a search engine. But nonetheless, I'll go to Google. All right, so in Google, let's type Geogebra. Geogebra. I'll pick the graphing calculator because it's the one I know how to use best. And let's just click on here. Now, the way you write them in here is interesting. Let me come back here as an example. Let's graph the following vectors. And let me give each of them names. So we'll start with U. Notice the arrow on top of there indicating it's a vector. I'll graph 1, 2. V will equal -3, 4, and then W will equal -5, -10. So all three of those are in R2, which means they're all in the regular plane. Let me go ahead, give myself space here, but let me come back to Geogebra. All right, the first one was 1, 2, and it was called U. So in Geogebra, you type U equals, and then you put parentheses, and then 1, 2, and when you hit enter, well, I didn't even hit enter, but even before you hit enter, you notice it draws a little arrow, and it has it going to the point 1, 2. If you hit enter, it'll take you to the next line, and look, it does. That's its version of a vector notation. We don't use the same thing here, but there are lots of books that use these curly brackets as notation. What was the next one? V was equal to -3, 4, and there you see it firing off in this direction. Notice that the tip of the arrow is at the point -3, 4. Same thing over here. U, the end was 1, 2. And then if you hit enter, it'll label that thing. And then finally W was equal to, that one was -5, -10. Let me hit enter. Now, down here, this is a little palette for typing in various other types of things if you don't have enough power to, or if you don't have what you need to type in an equation. This gives you a lot of extra stuff. But let me exit this and see. Oh, I can't see it all on one screen. Let me see if I can move this up. Oh, I didn't know it would let me do that. Maybe if I just first hit enter, lock it in. I think that locks in place. Notice too, it's got a weird outline about it, but if you click, it'll become normal. And you can decrease its size over here, so let me do that. Perfect. You can even relabel all of these things so that it's more helpful to you. But that's all I want right now. I just want a picture of them. So let me go ahead and copy this. This is the beauty of the OneNote program. It allows me to do this. And if you wanted to, you can even change the colors of these things. It tells me it's copied. Now let's go ahead and throw it in here. And you can make it bigger or smaller depending on what you want to do. But what's important to me is this point here at the end of that vector is 1, 2. This guy right here, the tip of that vector was -3, 4. And finally, the tip of this vector here was -5, -10. Notice the vectors all start at the origin. So the origin is a point of origination for all three of the vectors. And so let's get an idea, get comfortable with drawing these things. Just to draw them, you've probably may have had physics and you had to do this before to track like not just acceleration, but like the force applied to different things, pushing them up inclines. You know, when the direction and the magnitude were important to you, you indicate the length of the vector is the magnitude of the force, say, and where it points is the direction. So a lot of times the point x comma y is at the tip of the vector xy. Sometimes, though, the whole point of this is that sometimes the book or classes will not differentiate between the two, and that is fraught with some problems, but as long as you keep track of the context, you'll be okay. Just remember the vector is this arrow looking thing and xy is a point. let's try to graph one in R3. Now, I don't know how to use Geogebra for R3, so I'm not going to do it there. I'm going to try to do it by hand. So let's graph the vector. Here we have u equals 1, 2, 3. And this thing, when I put this symbol, that means in. So that vector is in R3. If you want, we're talking about three-dimensional space. So the graph of this, it's not going to be a great graph. I do leave graphs like this to computers because they're so, you can say I can't even draw this anyways. Y, X, Z. I usually allow computers to do this because it is such a pain. But what I'm going to do here is mark off 1 on the x-axis. On the y-axis I'll mark a 2. And on the z-axis I will mark a 3. So here's how you do it. What you do is you locate 1, 2 in the xy plane. So I have it right there. So I can, oh, I don't want to do that. Let me do, so you kind of do these dots like this to indicate this is the base point. Now that's not actually the point. What I'm going to do is raise it to a height of 3. So that you can do this. Oh, let me make it better. That's not good looking enough. I wanted to get, so that gives you a look that it's in three-dimensional space. That's how you do it. Now what is the vector? This point that I put there is the point 1, 2, 3. The vector that I'm trying to graph starts at the origin and draws a line till you get to that point, or a line segment, and there's the arrow. That thing is u. You can see graphing in 3 dimensions gets complicated very fast, so I try not to do it very much. Of course, let me put some things down. R1 is the same as R, the real numbers. R squared is the plane, the xy plane, in fact. R cubed. This is what I call three-dimensional space. This is the world we operate in. And when n is greater than 3, r to the n cannot be visualized. So what we're going to do when we talk about r to the n, we're talking about abstraction. We're trying to see the things that work in our normal everyday lives, like R2 and R3, that we can extract or generalize to n dimensions. Even though we can't visualize n dimensions, it usually it is useful in a vast array of applications. Typically long equations, systems of equations, and things like that. All operate in Rn mostly. R2 and R3 are good for us, but generally speaking, that's not the way that scientists and engineers have to operate. Unless, of course, they're making a building or something like that, then of course they do operate in those dimensions. For a notation, vectors, I'll usually write like this. I'll put an arrow above them. So anytime you see any kind of a lowercase letter with an arrow on top of it, you know I'm talking about a vector. Now textbooks don't do this for the most part. What they do, I'm going to have to see if I can make this work here. In textbooks, let me write this, textbook vectors look like the following. It's the same kind of a thing, except, well, let me come back here. Let's choose my thickness. They do something like this. So they would look like U, V, W, Okay? They're not quite as bold, but I'm being exaggerative, but they use bold letters. I can't go up here and do this all the time and maintain my sanity. So I am going to stick with these. Just note that your textbook uses the bold letters. On exams and things like that, when I made up exams on paper, I used bold letters for them as well. They're a lot easier because all you have to do when you're typing is type Control B and it makes it bold. So no big deal there. But here, it's pain. And almost certainly, whatever math classes you take on a chalkboard or a whiteboard or whatever, they'll use the notation that I do. So we're going to start looking at properties of vectors, and I'll keep it small for now so you can get an idea. And I think it's still a little bit bigger than I want it to be, so I'm going to make it one less. So I said, for a lot of my examples, I'll use R2 and R3 because you're familiar with the look of them. But these rules all work for Rn as well. So let's try this. I'm going to start with U. This is going to equal x1, y1. So x1 and y1 are real numbers. V will equal x2 and y2. So my example is in R2. Then when I add them together, we add them in the following way. Like so. Continue. This is actually equal to a single vector because we end up adding the x parts together and the y parts together. And that cross was not meant to happen. So this is what we call vector addition. And we call it component-wise. That means I add the first entries together and I add the second entries together, and if I had more, I would add the third, the fourth, all the way up to whatever n happens to be. So in particular, if I had u equals x1, y1, z1, and v equals x2, y2, z2, then u plus v would be the sum of the first components, the sum of the second components, and the sum of the third components. And oftentimes, so this is R3 here. Let me go ahead and put these. This is R2. This would be R3. What do you do about the situation in Rn? Because if you don't know what n is, how do you even deal with it? Can you talk about it in general? Well, what we do is the following. And I'm going to change my notation also. You'll find that it's kind of necessary to do when you have more than three things. So I'm going to let u equal the following. What I'll do is I'll write this. I'll write x1, x2, and then I'll do dots, like so, xn. So there's n components, but I use the three dots as a means of saying to myself, I don't know how many there are, but I'm using the three dots to take care of what that possibility could be. And then if I do v equals, so if I used x's for those, it's probably not a bad idea to use y's for these. And then when I add those together, I will add them component-wise. So I'll have x1 plus y1, x2 plus y2, xn plus yn. Let me make my x better looking. So this is how we handle a more general situation where we have n, a number that we do not know its value. We can use the 3 dots and ellipses to let us fill in the unknown. Next we come to scalar multiplication. So what I'm going to do is let's say if R is a real number and U equals x1, and I'll do this shorthand even shorter than I did before to indicate that I have n components. So I didn't draw x2, just x1 up to xn. I don't exactly know, but this thing is in Rn. You'll find this is the notation that is most often used in textbooks and things of that nature. We define the following. If I want to define R times U, what I do is I do R times x1. Now R is a real number and so is x1. And as I said that, I put that on there. Then we have R times x2, R times xn. So basically we just multiply R to each and every component in the vector. As an example, if U is equal to -8, 4, so that is in R squared, R2. Then when I do 4 times U, that equals -32 and 16. I basically just multiply each and every component by 4. If you have V equals 9, 0, and A, I don't know what A is, but it really doesn't matter. So this thing is in R3. Then -8V equals, let me see, I'll get -72, 0, and -8 times A, whatever that A was. If R is in R, so if R is a real number, we call R a scalar. The reason why is because when you multiply R times a vector, as we saw before, the length of the vector is adjusted. It gets longer by a factor of whatever R is. So if I multiply a vector by 2, the vector is twice as long. If I multiply a vector by -5, the new vector is 5 times as long as it was before. So multiplying by a real number scales the vector from short or long depending on what you're multiplying by. So that's why we call the vector or these numbers scalars, because of their scaling ability. Now, also, when I write this, this would be in Rn. Each number x sub I in that list is called a component of U. Another example, suppose the vector U equals 2, 5, and that's in R2. Let's graph U 2u, and negative u. So I'll go back to my Geogebra. I might graph them each separately. Let's go ahead and do that. Pop into Geogebra, and to get rid of these, you can just go to these arrows, this thing over here, and delete them. So let's come back here, and oh, look at that, it's nice. It allows me to change them component by component like that. That's very nice. So now you can see that it has drawn it and it ends there. What I might do, let me zoom in a little bit because I want a little more detail, and then you can move this around, of course. So you can see that vector, the tip of the vector is at 2, 5. So let me go ahead and bring that in. So you can see that it ends when we get to 2, 5. Let me put that up there. That point is 2, 5. Now 2u is going to give me a vector that's twice as long. That doesn't mean it's going to, well, it will, you know, when I multiply by 2u, I will end at the point 4, 10. So let's go ahead and graph 2u. So what you can do in Geogebra is the following. I have to give it a name. Well, I don't even know if I have to. If I do 2 times u, it does it for me. Does it give it a name? See, but it gives it its own name. I am going to put, if I click here, it won't graph the original one, and it will graph this one. I think I'm going to have to make it smaller, just not bigger, smaller, to make it viewable. There it is, right there. Now, unfortunately, because I had to resize it, well, actually, because I had to resize it, it's not going to look twice as big, but you'll see what I'm talking about anyways. So let me go ahead and copy it into here. And this time, as I said before, this ends at the point 4, 10. This vector is twice as long. The negative out here will simply change the direction of the vector. So let me come here and do negative u. It'll give it its own name, probably w. There it did. And then I won't show the v. If I click here, and I'll zoom in a little bit, you can also move this around. You can do all sorts of things. Let's go ahead and copy this in. So there we have it. And as suggested, if you multiply both components by -1, this point ends at -2, -5. So this guy right here, v was equal to 2u, and this guy here, this w, was equal to -u. So notice it points in the opposite direction as u does. And that's kind of the way that they work. The number that multiplies out there also can change the direction of the vector if it's negative. If it's not negative, if it's a positive number, it won't change the direction of the vector, but it will adjust the length of it. Another example here. Let's graph u, which equals 2, 5, v, which equals -4, 3, and then I want to graph also u plus v and u minus v. So let's take a look at how this works. So let's go ahead and put them in. Let's start with u and v and see what happens. So, oh good, I have this. I'll put it back in there. Now this guy, I'm going to edit. We wanted v to equal, let's see if it lets me go down there. It does not. So I'm going to, this was -4, 3. So, and I want it, I don't know why I did that. This guy right here I'll delete. And then those are the two that I want. All right, so let me click out here. Now A is equal to u plus w. That's fine. So here are our vectors. Notice that when I add these two together, I have 2, 5 plus negative 4, 3. 2 minus 4 should have given me negative 2 because it did u plus w and not u plus v. There we are. So 2 minus 4 is negative 2. 5 plus 3 gives us 8. Let me bring this down and copy all of them in. And you'll also notice a rule when it comes to adding these things. Like I said, some of you have probably seen these things. Even if you haven't had physics, you probably covered this stuff in trigonometry somewhere. So here's what I have. U and V are pretty obvious. And then A equals U plus V. So we've got that there. Notice this little thing, though. If I attach a little u here, that's the beauty of vectors. We allow them to start. Really, they don't have to start at the origin if we don't want to. You can move them around. It's only important that they start at the origin in different applications that are not covered in this class. So, but it's usually best if you're told to graph them to start at the origin. But you notice this guy right here is just like u. And then if I draw this here, another thing like this, this guy right here is just like v. So notice it forms a parallelogram, and the sum of this vector and this vector is not just where you add, you can see where you add the components together, but it's not just that. Graphically, the sum of the vectors is the length of that diagonal formed there. Let's do u minus v. So here I'm going to fix this to a minus, and there we have. And also you can see that this vector ends at 6, 2. So if you take 2 minus negative 4, you get the 6, and 5 minus 3 is 2. So that kind of has its own thing as well as far as these are concerned. Check this out. Let me come back and draw that picture sort of like this. Suppose I have a vector. Let's call this u. And this one v. Then if I copy v, and then I copy u here, this guy right here, from this point here to this point, this is u plus v. They call this the Parallelogram Rule. Now, I can draw the same picture in this way. Let me draw it again. I think it was a little bit longer too, wasn't it? So let me fix that. Yeah, it spanned 3 of them. And then V I'll also make a little bit longer. A little bit off, but here I'm going to call this W instead of U plus V. We do know that W equals U plus V. That means that U equals W minus V. So when I draw a picture here, notice here's my W, here's my V. W minus V equals this one out here. And I can change this also. V can equal W minus U. And you can see when I look at V is equal to W minus U. So they can all be tracked, if you will, on the in the parallelogram rule. Now, you may have seen an alternative to adding vectors like this. As an alternative, we can take, let's say I take my vector v, like so, and I can actually attach the u to the end of it. And then when I draw from here to here, that's u plus v. So notice here then that the vector u started right at this point instead of back at the origin. But this point right here, or this vector here, is still the sum of them. And you can see that too. If you look back up at these things, it's still going to be the length of the diagonal of a parallelogram. If I were to draw the rest of it, you can see that that's going to be the case. So sometimes it's convenient to move vectors around depending on what you want. But more importantly then, we can also draw a picture like this for subtraction. So all you do to get one for subtraction is, instead of call this diagonal u plus v, we'll just call it w. This was v, and this was u. We know that w equals u plus v, and same deal as before. U equals w minus v. Let's take a look at it. So this u right here equals w minus v. It's a little more convenient when it's like this. So u is the third side of a triangle, if you will. Or I could go and look at v. V would be w minus u. So v is the third side of a triangle. It's just the other side. These are typical in physics problems that I've seen when you need to put vectors back to back. If you're pushing something up an incline or whatever, if you need to know the direction and how much force is applied in that direction, this is much more useful than starting everything at the origin. So both of these situations can be very, very useful, just depending on the situation. Sometimes it's easier to do this than it is to start everything at the origin. The next topic is the length of a vector. How long is it? That's all we're asking in this situation. And you may not know this, but if I look at the absolute value of a number, did you know that it's equal to the square root of r squared? Did you know that? A lot of students don't know that. But even so, now you do if you didn't. What happens here is, if no matter what the value of r is, we know that the absolute value basically takes a negative number and makes it positive. It leaves any non-negative number alone. Well, that's exactly what this does do. No matter what r is, if it's positive or negative, the first thing you'll do is square it. So whether it's positive or negative, once you square it, it is no longer negative. We know that for a fact. And therefore, I can take the square root of it. So that is the definition, if you will, one of the definitions for the absolute value. Well, they do it also for vectors. Like if I wanted to do, I could do this. Suppose I let u equals xy. Then the absolute value of u equals the square root of x squared plus y squared. So you can see that I am generalizing the notion. This is in r to the 1. This is in r squared. I can continue. Suppose v is x, y, z. Then the length of v is the square root of x squared plus y squared plus z squared. And as you might be able to imagine, if w, so this is in R3, And if w equals something so like this, I think it's x1 up to xn, then the absolute value of w is the square root of x1 squared plus x2 squared plus all the way up to x sub n squared. So you can see that in n dimensions, while we cannot visualize a vector even, we still have a notion for its length. Notice that we use the absolute value depending. And the absolute value will make sense depending on the context. I can't just say the absolute value of something and you know what it means. But if you know it's a vector, then at least you know that you're going to square the components, add them together, then take the square root. Now, one of the things, this section is so crucial to the your success in the course that I want to spend a lot of time on it. And one of the things that makes this course difficult is that the students are required to have some theoretical knowledge of the material. That means taking and proving certain things. Most students who have been through calculus will simply brush past theorems, but they might memorize the name of the theorem or what it stands for, but they won't actually understand the proof or attempt the proof. That's not going to cut it in this particular class, but we're not going to require you to do heavy proofs. We're going to start somewhat light and build our way up to stronger proofs. This is an example of what I'm talking about. All right, let's prove that if U is a vector in Rn, I get a little lazy when it comes to those things. I shouldn't. So let U be a vector in Rn and let R be in the real numbers. The length of R times U is the absolute value of R times the length of U. And let's prove that. So typically what you might write to indicate that you're going to prove it is something like this, proof. So let's go ahead and do it. Let U equal x1 dot 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 xn. So I'm not specifying what it is. I'm just giving a general label for any typical vector in R to the n. So we're going to let that U equal that. And that implies that RU equals, so we're going to multiply each and every component by R. Now, then the length of RU is the absolute value of RU. So RU is a vector itself. And be careful with your arrow. Don't let it encompass the R as well. But what we do then is we add up the squares of each component. So we'd have an Rx2 squared, and it goes all the way until we get to Rx sub n squared. So by definition, that's the length of the vector. Now what I'm going to do next is rewrite some things in here of R squared x1 squared plus R squared x2 squared plus all the way up to R squared x sub n squared. And now I'm going to factor out R squared from all those things. You notice I'm not writing any details off to the side of the page because all of this stuff is pretty evident. I think everybody knows what I'm doing here. It's just your basic algebra. Now, it's important when you have the square root of the product of two numbers, you can't just break a square root up because those numbers could possibly be negative. So like, as an example, I can take the square root of 16, right? But 16 could be negative 4 times negative 4. The square root of 16 is not equal to the square root of negative 4 times the square root of negative 4. So I can't break it up. However, I can break it up in this case here because I know that neither r squared nor the other piece is negative. So this is perfectly fine. Well, you should recognize the absolute value of r. And then this part here, this square root part, is by definition the absolute value of u. So, and that's exactly what I said. This is the absolute value of r times the length of u. That's exactly what I was trying to prove. So you can put a little, I've seen this where people put this kind of stuff. I'm never going to do that kind of stuff. Or they'll put a little block or whatever to indicate that the proof is over. When I'm done, I'm just done. So I'll go on to the next thing now. So that's the nature of what I'm talking about here. Each statement is a logical statement, and you're trying to use logical statements to get to the conclusion. So next we'll look at the arithmetic of r to the n. So as I write all of these things, we are going to let u, v, and w all be vectors in Rn, and let c and d be scalars, or just real numbers. So 1, here's the rules. 1, if I take u plus v, that's going to equal v plus u. The order that I add them doesn't matter. So this is the commutativity. Next, if I decide to add u and v first, and then add w, I could instead add u to the sum of v and w instead. So in the second, I would add v and w first and then add u to that. This is called associativity. And you'll find most of the rules are familiar to you. The context is just a little different than before. 3 u plus 0 with an arrow above it just equals u. So this is like an additive identity. And in case you need this, 0 with an arrow above it is called the zero vector. That means every component will be a 0. Notice that's not the same as the number 0. The number 0 only has one component. The zero vector has multiple components. Next, if I do u plus negative u, I should get the 0 vector. Just like if I took a real number and added its negative, I would get the 0 number. So this could be called additive inverse. And we should probably be careful here too. When I write negative u, if you want a definition that you can hang on to, that's -1 times u, which means that I will multiply each and every component of u. What was u? Well, let's do this. basically I'm putting a negative in front of every component inside of the vector u. So it should make sense when I add these together that I'll get a vector of all zeros. Now let me involve the scalars. If I take a scalar and multiply it to the sum of two vectors, I can distribute it as so. So this is distributivity. And I can also, it doesn't matter, well, I think this may not be the same, quite the same as distributivity, but if I take the sum of two real numbers and then multiply it by a vector, I can also break across that summation as well. So that's another version of distributivity. Then we have number 7. If I take a real number times du, where d is also a real number, I could instead do cd first and then multiply that to the vector u. So that's a form of associativity. And then this one shouldn't really need to be written, but it is. If I take 1 times u, I'll get u. Because 1 times u, all you're going to do is multiply every component by 1, and that doesn't change anything. So let's prove some of these things. And your book will have you do some of them as well. I just thought that I might do a few of them to give you an idea of how these things look. So let's see, I'm going to choose to do the first one, the commutativity. So I want to prove that u plus v equals v plus u. And so here's how the proof looks. What we can do is let u equal u1 up to un, and let v equal v1 up to vn. Okay, so these are full sentences too. When you do write a proof, they're usually full sentences because the equal sign can, at the very least, satisfy that you need to have a verb in each sentence. So anyways, when I do u plus v, we know that we add the components together. So I'll have u1 plus v1, un plus vn. Now I want to change the order. Now watch this. This equals exactly opposite of what I wanted to say. This equals v1 plus u1, vn plus un. I'm able to change. The reason why is because the real numbers themselves is commutative under addition. So you've known this about real numbers your whole life. You know that you can switch a plus b equals b plus a when you're talking about real numbers. So all I did was use that to switch the order of each of these components. Well, this is very nice. I can break this back up into u1 up to, I did it again, v1 up to vn plus u1 up to un, and that equals v plus u. So I'm finished. Let's try another one. This is the one that says u plus negative u equals the 0 vector. So if I'm proving this, again, I will do the same thing that I did before. Let u equal u1 up to un. Then, when I do u plus negative u, that equals, let me write down my u again, u1 dot 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 up to un. But when I do the negative u, I've already discussed that that just makes each component negative. So when I add those together, I add component by component. We'll end up with u1 minus u1, un minus un. But that's equal to 0 dot 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 0, which equals the 0 vector. How about number 7? Here we want to do this associativity rule. Well, let's give it a try. Remember, C and D are real numbers. Once again, so let's see what C times du looks like. If I do C times du, that means I'm going to do C times d u1 up to un. Well, since I'll do the parentheses first, the order of operations is still valid no matter where we're at. Of course, when I multiply through by d, I'll drop the parentheses because I don't need them anymore. So d is being multiplied to each component. Now, by definition, the c will multiply to each component inside of there, so I'll get cd u1. And since I multiplied c times du1, I've already multiplied the d and the u1 together, so that's why the c is outside of the parentheses. Now, this is typical for proofs. Now, each of those components, each one of these, where did my mouse go? Each of these components here, we're talking about real numbers here. C, D, and U1 are all real numbers. C, D, and UN, they're all real numbers. And we know that in the world of real numbers, multiplication is associative. So I know that I can change the parentheses to be around CD. Now I can pull the CD out, like so. And of course then that equals CD times the vector U. So you get the idea. Basically, all of them are using the general rules of the real numbers as we work them. Otherwise, I mean, look, what these are doing is it's generalizing smaller dimensions into larger dimensions. That means a lot of the things that worked in the lower dimensions will still work in the larger dimensions. And that's what this whole thing is about, generalizing what we see every day, 2 and 3 dimensions. Now, one of the, perhaps another giant important concept in this course is the idea of linear combinations. These are very important. So we'll do this a lot. Let's let C1, C2, up to Cm all be real numbers. And I also want to let U1, U2, up to Um to all be vectors in Rn. The expression C1U1 plus C2U2 plus CMUM is called a linear combination of the vectors U1 up to UN. M. I gotta be careful. A lot of times I gotta watch because N, I'm using the N for the number of components. M are the number of vectors. So I gotta be careful. A lot of times I'll swap them and that will of course ruin whatever I'm trying to say. The numbers C1 up to CM are called weights or scalars. Usually they'll talk about scalars when you're talking about one vector, and in something like this they're called weights because if you've ever done a weighted mean or a weighted average for something, you take weights into account in the average. So let's take a look here. Let me come back to Geogebra. I'll get rid of these other ones for now. And I want to show you what some linear combinations look like. So let's say I do 2u minus 5v. What does that look like? I shot way off there, didn't it? There it is. Oh, wow, is that long? Okay. Oh, it has the answer right here, 24 negative 5. Let me make the page a little bit smaller so I can see it. But I really want, there it goes. Now click in here. And then you can also, there's some other things, like if you go right here, I can go to the settings and I can change the colors if I want to, but I can also take and get rid of the name if I want to. The reason being is I don't want the letter that they're using there, I want the one that I'm using. So this is the output vector. Let's go ahead and copy that. So here is an example. I've got my U and my V. I don't remember what it was. Was it 2U minus 5V? So this was 2u minus 5v. So that's a linear combination. Notice that what the output was a vector. Let's do some other, just a few others. I want you to see what the outputs are. You can actually compute these if you want to. So what you do is take 2 times each component in U, and let me put this down so you can do it later. I think this was 2, 5. And V was equal to negative 4, 3. And then this was the linear combination of it, so it's also a vector itself. Let's try another one. Let's do, let me get rid of this. Let's do negative 0.1u plus 3.2v. Enter. And there we go. So the same kind of example here. This one was, let me come back again, it was negative 0.1u. So negative 0.1u plus 3.2v. And you can see where they end here. If you look at this one right here, you can try it. We ended up at 24 comma negative 5. So when you look at this, it was 2u minus 5v. The 2u was 410. And the 5v, let's see what that was negative 20, 15. So now when you subtract them, you do get the 24, negative 5. So I'll let you do the other one on your own. You can see what's going to happen there and track the ends and everything like that. Given a vector v many times, we try to determine if v is generated by the vectors u1 up to um. So what does it mean to be generated by those vectors? That means there are real numbers or scalars C1 up to Cm with V equal to the linear combination of the U's, using those weights, if you will. Whenever I think I need a little more info, I'll fill in more before I put my 3 dots. So that's what we call V is generated by the vectors U1 or up to UM. In other words, V is a linear combination of U1 up to UM. So you can see linear combination is just beginning. It's like a snowball. It just started. And it's going to get bigger and bigger and bigger. So make sure you get the feel for it right now before we go any further. Let me do a couple of examples to end off this particular video. So we're going to start with U1 is going to equal 1, negative 2, 2. U2 is going to equal 0, 5, 5. And then U3 is going to equal 2, 0, 8. So all 3 of these things are in R3. And then I'm going to let V equal negative 5, 11, negative 7. So what I'd like to do is determine if V is a linear combination of the U's, or in other words, determine if V is generated by U1, U2, U3. So what does that mean? Well, when I go to solve this, we need to find real numbers, C1, C2, and C3. I'll do that just to, even though I already said real numbers. We want to find numbers C1, C2, and C3 with V equals C1U1 plus C2U2 plus C3U3. Let me continue this. This is C. Let me put in my U. That was 1, negative 2, 2. That was C1. Then we had 0, 5, 5. C3. What was that? 2, 0, 8. Let me put my vector in there. That was V was equal to negative 5, 11, negative 7. Here you're going to see where everything starts to come together. Let me go ahead and multiply my constants through. Keep this side as it is. So over here, I'll have C1, negative 2C1, 2C1. Now adding the vectors all together and making one big vector on the right side, I'll have C1 plus 2C3. That 0 doesn't mean anything. Then we have negative 2C1 plus 5C2. And then finally I have 2C1 plus 5C2 plus 8C3. On the other side I have negative 5, 11, negative 7. Now, two vectors are equal if and only if their components are equal to each other. So I have a sequence of equations. Try to spread it out so you can see. So for example, this first row here is equal to negative 5. Then my next component here, this second component, is equal to 11. I think I'll move that addition sign here closer to the C3 because I kind of want it out of the way. And then finally we have 2C1 plus 5C2 plus 8C3 equals negative 7. Oh, this middle one was equal to 11. So what we have then is the vectors. I had an equation involving vectors. That leads to a system of equations. And we know what to do now. Now all we've got to do is convert this to an augmented matrix. And I'm going to work this just like I do any other thing. And I'll stop when I see there's obviously no solution, but I will keep going until that's obvious to me. So what's going to happen then is I'm going to first wipe out this negative 2 and this 2 down here. So the way to make that happen is I can take 2R1 plus R2. When I'm all said and done, I know this is what's going to happen. Since I'm using R1 to add to things, it's unchanged. And now let's take a look at what happens. So 2R1, so 2 times, well, that doesn't do anything. So I know that 0 is not going to change anything. So that's nice. All right, then 2 times 2 is 4, plus 0 is 4. And then 2 times negative 5 is negative 10, plus 11 is 1. And then over here, the only thing I got to worry about is these last two pieces. So 2 to get this, to take this 1 and wipe out that 2, I need to do negative 2r1 plus r3. So negative 2 times 2 is negative 4 plus 8 is 4. And then down here, negative 2 times 5 is 10, minus 7 is 3. Well, I can see that I'm not going to have a solution, but what I'm going to do is take negative r2 plus r3. That'll wipe out the coefficients for the third row. So I'll do negative r2 plus r3. And let's see what I have. No solution. So what did the question ask? I got to go back, way back to the beginning. It says determine if G is generated by those vectors. So we now know that V is not generated by U1, U2, and U3. In the next video, we're going to go much more heavy into this idea of being generated and spanned and all that kind of stuff.